This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning everyone. So today we're going to continue looking at examples of controller design from the perspective of achieving desired open loop transfer function characteristics. Okay, so we can think of the sorts of performance specifications as relating to steady state, desired steady state behaviour, and that's all about the shape of the open loop transfer function at zero frequency, right? And we can think of performance in terms of the desired transient behaviour of the closed loop, and that's more to do with what's happening to the open loop transfer function around the frequency where the magnitude of the open loop transfer function will be 1, so the so-called crossover frequency, and the phase margin. Okay, we left off last time thinking about what might be done with a lag compensator, and a lag compensator has this form here, and it's something that we typically use to achieve desired open loop transfer function characteristics at low frequency, right? Without doing much about what happens around the crossover frequency. In fact, the way these are typically designed is such that all of the action happens well below the desired crossover frequency. All right. So in these examples, we've been thinking about steady state characteristics, and that's often, that's really just about, what happens at zero frequency. And we've got a parameter K here, which allows us to increase the gain at zero frequency in order to achieve desired steady state error specifications for step and ramp type inputs to the closed loop system. All right. The transient specifications relate to crossover, and we can translate time domain specifications into specifications on the crossover frequency and desired phase margin by thinking of the complementary sensitivity function as having the characteristics of a canonical second order system. Okay, we've seen how to relate damping to phase margin and crossover frequency to the natural frequency by virtue of the time constant of canonical second order dynamics being related to 1 over the damping times the natural frequency. Okay, so the thing to be careful of here is that intuitively, you would think that by increasing omega c, you'll increase omega n, but that won't necessarily lead to a reduction in the settling time, which relates to this time constant, because increasing omega c, which increases omega n, might make the damping smaller, right? So by increasing omega c, you might be making omega n bigger, which will tend to reduce this, but at the same time, you might be making psi smaller, which will tend to increase this, and the effect will cancel each other out, and you don't actually get any reduction in the settling time. All right, so that's why we've got to look at these curves to figure out the required relationship between the natural frequency of the desired second order dynamics and the crossover frequency in terms of the damping. All right, and what we were doing in these examples, and they really are just examples, is seeing how to determine the coefficients or the parameters of the controller by writing down relationships that they must satisfy in order to achieve desired phase margin and to achieve a particular crossover frequency. Okay, so these sorts of calculations. Here, for example, was just about making sure that we've chosen one of the parameters, the only one that was left after choosing the others to meet these sort of specifications, to ensure that at the desired crossover frequency, the magnitude of the open loop transfer function is equal to 1. In the case of a lag compensator, we're relying on the phase of the open loop plant at the desired crossover, giving you enough phase margin. Okay? But really all we're doing is just writing down some equations here that are consistent with the specifications in order to determine the controller parameters. So a PI controller is just a special lag controller, right? The way to go about this, the design of this is exactly the same as a standard lag controller, okay, given phase margin and crossover specifications. Okay, and really all we're doing is relying, in this case, on the open loop plant transfer function having a phase that is consistent already with our desired phase margin. We're accounting for the fact that a lag compensator is always going to give you some phase lag, and if we make sure that the crossover frequency is a decade above that, the amount of phase lag that is pushing us closer to minus 180 will always be less than 5 degrees as it arises from the controller. Okay, and then choosing the other parameters to make sure that the gain of the open loop transfer function at the desired crossover frequency is equal to 1. All right. So let's now look at what you can do with a phase lead compensator and how you might go about choosing the parameters of the lead compensator to achieve specifications. So the difference between a lag and a lead compensator is that the lead compensator has a 0 that's closer to the imaginary axis than the pole. Okay, so that's what this is telling you, right? The 0 is at minus 1 on tau z, the pole is at minus 1 on tau p. All right, and you can see that what a phase lead compensator does is it adds positive phase to the open loop transfer function, right? And if you line up where it's adding positive phase to around the desired crossover frequency, right, which relates to the transient type specifications that might come with the problem, then we can use it to improve the phase margin to push you up away from minus 180 degrees, right? And the phase margin is about the difference between the phase of the open loop transfer function at crossover and minus 180, right? So phase lead compensators are used like that. They're used to fix up what's happening at the desired crossover frequency, right? Whereas a lag compensator is being used to fix up what happens at low frequency without interfering with what will be happening at the desired crossover frequency. All right. So, again, this is just an example to illustrate how you might go about writing down some equations in order to determine the parameters of the lead compensator in order to meet some specifications. It's by no means a recipe, it's just an example to illustrate how you might go about calculating the parameters. All right? So let's say we've got a plant like this, a pole at S equals 0, a pole at S equals minus 20. All right? We're after a steady state error for a unit ramp reference input that doesn't exceed 0.1. Okay, let's suppose our transient specifications are consistent with having a phase margin more than 50. That's quite a substantial phase margin. You wouldn't expect to have much oscillation in the closed loop step responses. And a crossover frequency of more than 40 radians per second. So that's going to be pretty fast. You would expect, with the phase margin being this large and the crossover frequency being 40 radians per second, for the settling time to be quite short. Okay. In order to, there's 3 parameters here, right? So we can push this up at all frequencies by the same amount by increasing K. All right. That's the only way we're going to be able to get the required gain at DC, right, to meet steady state specifications. This is our steady state specification. This is really just coming from the fact that at steady state, right, we want the error, at time, in steady state, so at time equals infinity, which is given by this, which is, just the final value theorem, to be less than 0.1, right? So all of this is just collapsing this analysis in here, which is saying, well, the error signal is just the output sensitivity function times the Laplace transform of the input. The input in this case is a ramp. So its Laplace transform is 1 on S squared. All right, this is just the closed loop sensitivity function that maps the input to the error signal. All right, we know by the final value theorem that the steady state value of the error will be the limit as S goes to 0 of S times the Laplace transform of the error. That's what it is. This is just substituting in what the controller is, right? It has the form of a lead compensator, a 0 and a pole and a gain. All right, there's your plant transfer function. Manipulating all of that, you end up with the two S's on the top here that cancel out the S squared coming from the ramp input. All right, and as you take S2 equal to 0, you just get the 20 divided by 100k left on the bottom, and you want that to be less than 0.1. All right. So, that's how much we would have to scale the gain of the open loop plant to achieve this specification. All right. But if you just multiplied the plant transfer function by a constant gain equal to the smallest required to meet this specification, you would get a crossover frequency that's much less than the required. Okay, so we're actually going to have to use more gain than the minimum required to meet our steady state specification, right? If we were to just use a constant gain controller or even a lead compensator, by increasing the gain of this, we're going to push the crossover frequency to the right. Okay. The problem with just using a constant gain compensator is that as we increase it in order to push the crossover frequency to the right, we may, to achieve a crossover frequency of 40 radians per second, if we were just relying on the phase of the open loop plant, right, because we're not doing anything with a constant gain controller, you would get a very poor, you would get a phase margin that's not consistent with our specification, right? So this would be a phase margin of like 26 degrees. Well, that's less than what we need, right? So we can use the pole and the 0 of the lead compensator to add phase, right, at the desired crossover frequency. In order to exceed our specification, we need at least 24 degrees of extra phase, right? And that can be achieved by choosing the location of the 0 and the pole, right, to give us the desired phase from the lead compensator. And what we're going to do is line this up with the desired crossover frequency, right? And this frequency here, in terms of these parameters, is given by this expression, okay? And the amount of phase we get there is given by this expression. So we know how much phase we need, right? That gives us one equation that involves tau z and tau p. And we know where our desired crossover frequency is, and we're going to line that up where there's maximum phase introduced by this lead compensator. Of course, how much you get depends on how you've chosen the location of the pole and the 0. Okay, so that gives us two equations in two unknowns. Okay, so in principle you can solve them. Sure, they're nonlinear equations, but they're not that hard to solve. In fact, if you took the sign of both sides of this equation, you would be able to write down what tau z is in terms of tau p, right? Which you could then substitute in here to just get an equation for tau p. All right? And then we're left with the one remaining parameter, okay, k, and we can now choose that to ensure that at the crossover frequency, the magnitude of the open loop transfer function is equal to 1, right? Because that's what defines the crossover frequency. Okay, if you just rearrange this and bring this up here and that down there and that up there, what we're really saying is k times g at the crossover frequency times the pole of the compensator evaluated at the crossover frequency, sorry, the 0, divided by the pole of the compensator evaluated at crossover frequency equals 1. That's all this equation is, all right? So we're just using the definition of crossover frequency to determine this parameter. We get a number that is consistent with our steady state specification, so we should be done. Okay. So this is showing what the Bode plots look like. These are the step responses that you get. All right. You can see here that if we were, this is what you get with the constant gain controller that would just meet our steady state specifications. The issue is that its crossover frequency is too low, right? So it's going to give us a settling time that's too long, right, according to our specifications. But if we increase the gain of the controller from, say, 2 to 10, that would push this across here, but it wouldn't change the phase plot, and you would end up with a lousy phase margin, right? So what the lead compensator has done is given us the blue loop shape, okay, which achieves the desired crossover frequency, but with more phase margin, okay? And we're getting the more phase margin here because the lead compensator is adding phase like this. All right, so you can use a lead compensator to fix up the phase at the desired crossover frequency. All right. All right. So again, it's important to check this because in the end, your controller has three your closed loop system will have 3 poles, right? Because we've got 2 in our plant, we've got 1 in our controller, right? So the number of closed loop poles you get will be the sum of the number of open loop plant poles and controller poles. Okay, so we'll have 3. We've probably arrived at these specifications by assuming dominant second order dynamics of the closed loop. So, but we've got 3 poles, not just 2, so it's important to check that you actually meet your specifications. All right. And so what we're getting here is the faster response because we've pushed the crossover to the right while maintaining a reasonable phase margin, right? Whereas if we'd just done that with a constant gain controller, pushed that to the right by increasing the gain, sure, we would have become faster potentially, but not necessarily with more oscillations, right? Okay, so far we've really just focused on steady state performance requirements and transient performance requirements in situations where you could achieve what you wanted with just one type of compensator, but maybe you can't always do that. It really depends on the situation that you're dealing with. And so it's perfectly reasonable to combine these things, right? So here we're combining a lag compensator, all right, this part here, and a lead compensator, and we could use the lag compensator to fix up what's happening at low frequency, and the lead compensator to fix up what's happening at crossover, right? So you can see that the lag compensator is always going to introduce some phase lag, some negative phase, so you want to make sure that where it's doing what it has to do, that's far away from the crossover frequency, and we can use the lead compensator to increase the phase at the desired crossover frequency to achieve our transient specifications. All right, and I guess it's worth noting that a PID compensator, which you probably hear about all the time within the context of feedback control, is just a special case of a lead lag compensator, right? Where one of the poles is set at s equals 0 and the other pole at s equals minus infinity. Okay, so these are just labels for things, they're not magic, right? PID compensator is doing what I just described. It fixes, it makes sure that you've got infinite gain at 0 frequency, which we know is important from the perspective of getting 0 steady state error for step type inputs, okay? And then the 0 gives you the phase lead, the other 0 gives you the phase lead, which you can line up with the desired crossover frequency. So again, this is just another example to illustrate how you might go about, figuring out what these controller parameters should be in order to meet specifications. Okay, in this case, we've got a plant that has 3 poles. They're all stable. Okay, one of them's at the origin. So you would already get 0 steady state error for step type inputs to the closed loop. But if you've got ramp type inputs, then you won't get 0 steady state error without doing something extra in your control. Okay. And here we've got a specification that we want the error in steady state to be less than a certain value. Okay, these are our transient specifications, which, assuming dominant second order dynamics for the closed loop, can be translated into requirements on the phase margin and the crossover frequency. Okay, So again, we can go about this by thinking about, well, how much gain do we need at DC to meet our steady state specification? The gain of the controller at DC is just K, right? So that's the only part of the controller that's going to help us meet the steady state specification. So how big does it have to be? Right, we'll go through the same analysis that we went through here, right, to get a bound on the gain, all right? Now, we've got a lower bound on the crossover frequency. If you chose, in this particular example, to set the crossover frequency at the lower end, right, so at 6, it turns out, but by following this procedure, that you don't meet your original time domain specifications, right? So I tried it, it didn't work out, so what I did was went back and said, well, let me ask for a little bit more, right? So I put it at 10, and I asked for a little bit more phase margin as well, right? Remember that these things are being translated to these on the basis of an approximation, right? And you know, if you push the limits too much, then the approximation may not work out for you, right? So one strategy is to ask for a little bit more than you actually need when it doesn't work out when you choose the bare minimum. Okay, so in this case, you know, let's say, well, let's choose omega c equal to 10. Well, that exceeds our specification, and a phase margin of 60, that exceeds our specification, right? We've got to do something with our compensator to achieve a phase margin of 60 at a crossover of 10, right? Because the uncompensated phase margin is too small, right? So this is how much extra we need. We're accounting for the fact that the lag part of the compensator is going to decrease the phase margin, right? So we're going to have to add something from the lead part to cancel that out, as well as give us the amount needed to achieve 60 when we're only getting this much from the open loop plant. Okay, so again, this is just, you know, giving us a number, right, that we can use to choose the lead part, the parameters of the lead part of the compensator, right? Again, we're following the same strategy. We're saying, well, okay, the lead part of the compensator looks like this. If we line the crossover frequency up here, right, then we get one relationship for the parameters that tell you where the zero is and where the pole is. That gives us one equation, all right? And then how much we need is going to give us another relationship between those two parameters to give us two equations in two unknowns that we can solve, right? So it's exactly the same thing as I did before. This is just rewriting this equation by taking the sign of both sides, right? To make it obvious that, you know, I know phi, so this tells me that tau p is some number times tau z1, which I can substitute in here to just get an equation for tau p, right? Based on lining up the crossover frequency with where you get the maximum amount. So this is just one way of doing things. You can line the crossover frequency wherever you like, right? Just, you know, it's easy to get an equation that tells you a desired relationship between these parameters by lining it up here, right? But it's not the only way to do it. Right? It's just an example. All right. So, you know, that fixes these two parameters. We're still left with all of these, right? So how do we go about choosing these? Well, we could try setting K to be 75, right? Because that'll meet our steady state specification. We want to make sure that the lag compensator is not going to interfere too much with what's happening at crossover, and certainly not interfere more than 5 degrees, which we've accounted for in this calculation here, and that will be the case if we choose the location of the zero of the lag compensator to be a decade below the crossover frequency. That'll make sure that the phase lag introduced by this part of the controller is less than the 5 degrees that we've accounted for here, all right? Which then just leaves us with one parameter, and the only relationship that we haven't used yet is the one that defines the crossover frequency in terms of where the open loop transfer function must have gain equal to 1, right? And so that's just what this equation is. It's saying, well, choose this parameter here so that lambda j omega c is equal to 1, right, to give us the final equation. Right, so we've set all of the parameters. Okay? So this is not the only way to do things. It's just one way, and I'm doing it. I'm showing you just so that you can see examples of how you might go about choosing these parameters to meet specifications. Okay? The other way to do it is just to sit in front of MATLAB and move the parameters around until you get the desired loop shape, crossing over the desired crossover frequency with the right sort of phase margin and so forth, right? Or you could think in terms of root locus, which is what we were doing last week, right? So I would encourage you, when tackling a design problem, to use all of the tools at your disposal, right? Not just try to look at examples like this and extract a recipe, because what has to be done really depends very much on the plant transfer function and the types of specifications you're trying to achieve, right? So just look at these as examples to illustrate the sorts of calculations you can do to fix the parameters of compensators in these very common forms, right? Proportional, lag, lead, lead-lag, PI, PID, right? What's important is that you understand what they can do for you, right? And so the main thing to remember is lag helps you fix up things at low frequency, lead helps you fix up things at crossover. Low frequency is about steady state performance specifications, crossover frequency is about transient specifications. Okay. Yeah, so you can see that what the lead compensator is doing here, what the lead part of the controller is doing here is bringing the phase up. Okay, giving you a better phase margin at the desired crossover frequency. Right, whereas if you just tried to do things with a constant gain controller, you would exceed your crossover frequency specification, but you would get a lousy phase margin. Right. So this is just an example showing you the same thing again for a PID controller. The approach is exactly the same as all the examples that we've seen so far. Right, a PID controller, strictly speaking, is not proper. Right, but you can make it proper by putting another pole in here with a very small time constant, right? And by making the extra pole here have a very small time constant, you'll make sure that it doesn't interfere with what you're doing with all of the other parts of the compensator. All right, so you can always make this proper by putting just a fast pole in, and by making it a very fast pole, you're not going to interfere with what you've set up with the rest of the compensator. All right, so, how do we go about choosing these parameters to meet specifications? Well, figure out what our specifications mean in terms of a desired crossover frequency and phase margin. That's about transient performance, right? Here we're using the pole to give us infinite gain at DC. So, the steady state specifications don't just relate to K, right? They might be achieved by virtue of having the pole at S equals 0, which gives you infinite gain of the open loop transfer function at DC at 0, right? Figure out how much additional phase is required to achieve your phase margin specification, right? In this case, this part is giving you the phase lead. This is going to give you the positive phase. This is part of a lag compensator, so together these things are always going to give you negative phase. So achieve your phase margin specification, you choose this parameter, right? The amount of positive phase that a 0 adds, right? Relates to the fact that, the phase of TZ1 J omega C plus 1, right, is going to be, arc tan omega C tau Z divided by 1, right? So that's how much phase it's going to give you, right? So you can use how much extra phase you need to achieve your phase margin specification to choose that parameter, right? Choose the parameter of your lag part of the compensator corresponding to the 0 to be such that, the lag compensator is not going to interfere with what you've achieved with this part of the compensator, right, by setting it a decade, the location of the 0 here, a decade below the desired crossover frequency, right? And that leaves us with one parameter, and we can get what that one parameter, we can set that one parameter that's left in order to ensure that the crossover frequency is where we want it to be. Right, so choose that parameter to make sure that the magnitude of the open loop transfer function at the crossover frequency is equal to 1. Okay, as usual, you have to go and check, right, that the original time domain specifications are met, right, because your translation of time domain specifications into a desired crossover frequency and phase margin is most easily done by assuming canonical second order dynamics for the resulting closed loop, but of course your closed loop may have more than 2 poles, right? And that sort of approximation is only valid if 2 of the poles dominate, right, with desirable damping and natural frequency. All right. You may have heard of things called Ziegler-Nichols tuning rules. Okay. These work well when your plant has a particular form. All right. One case is this form here. All right. So there's a system with first order dynamics and some delay. Right. These sorts of models often arise in the process industry. Okay. Which is where these guys worked in the 50s, right? The parameters of such a model can be easily identified from step tests, much like the sort of things you did in Workshop 3 to identify the parameters of your little Lego robot models. Okay, so you do a step test on a process in a chemical plant. You get a step response like this. Well, this is the delay that fixed that parameter. Right? How long it takes to settle will relate to this time constant here, right? And how much gain you get. If I put a unit step in and I get this out, that tells you what K is, right? And so these guys, figured out rules for choosing the parameters of a PID compensator, now written parameterized in a different way to this. So this is one parameterization of a PID controller. There's 1, 2, 3 parameters. Here's another way of parameterizing a PID compensator, right? The parameters are now different, but you end up with, still 2 zeros and 1 pole at the origin. Okay, and they figured out, rules for choosing these parameters in order to set the crossover frequency to be, 1 over the delay, right? And to achieve a phase margin of 30 degrees. So that's all that choosing these parameters does, right? It goes, you could go through this sort of process, right, to choose these parameters, but the objective in this case is just to get the crossover frequency to be related to the delay, and that's to make sure that the delay is not going to be introducing too much phase lag into the loop at the desired crossover frequency, right? They're choosing the rest of the parameters to make sure that you end up with a phase margin of 30, which is not really a very big phase margin. If you had a phase margin of 30, you would still get some oscillations in your closed loop response. If you want no oscillations in your closed loop response, you need a phase margin of like 70. Okay, but that's all these things are doing, right? Now, this works okay as long as your plant looks like this. But if your plant doesn't look like this, then choosing the parameters in this way will not work. So I wouldn't recommend, just blindly applying these magic rules, right, when doing control design. Okay, because, they won't work unless your plant looks like that. But they're getting to this by doing this sort of analysis, right, with, quite, not very aggressive performance specifications, right? You're only looking for a phase margin of 30, right? And the crossover frequency specification here is really not driven by a desired settling time, but making sure that the delay is not introducing too much phase lag. And we've seen, for example, within the context of Nyquist stability analysis, that having delay limits how big a gain you can have. It limits the crossover frequency, right? Before you lose stability. There's another version of the Ziegler-Nichols tuning rules. and again, it's just about, coming up with a rule for choosing the parameters of a PID compensator on the basis of things that can be determined experimentally, right? So what they do is they wrap a loop around the closed loop and they pump up the gain, right, of just a constant gain controller until the system starts to oscillate, all right? And that gives you, the numbers required to compute the parameters of the PID compensator here. Okay, so really the idea here is that you use a constant gain controller to push the closed loop to the edge of instability, right, where it just oscillates, right? So if you think about the root locus, it's like, drawing the root locus plot and choosing the value of k that puts the closed loop poles on the imaginary axis, and then you ease off, right? And you can see the easing off. I'll choose the gain to be half of what puts me on the imaginary axis. And by doing that, the idea is that, you'll get, some damping in your closed loop response, and hopefully it's consistent with what you want. And so they chose these numbers on, doing lots of, looking at lots of systems, mainly in the process industry. And, for those types of systems, you get reasonable outcomes. But I would, again, not advise just blindly applying rules like this. Why not do stuff like this, where you're using your understanding of what things mean to make design decisions, rather than just blindly following some rules. And the reason I'm emphasising this, because in my experience, lots of people just say, but there's this magic rule, and I'll just apply the magic rule, and then they're surprised when their controller doesn't work. Or design it properly based on your understanding of how things work. All right? Okay. So it's also important in control system design to realise that, your design objective is not just about meeting steady state specifications. It's not just about meeting transient specifications. There are other things that you need to worry about. You need to worry about the impact of sensor noise. You need to worry about the impact of modelling uncertainty, right? And those sorts of things typically place an upper bound, as we've discussed before, on the crossover frequency, whereas all of the things that we've been discussing so far put a lower bound on the crossover frequency. If I want a smaller settling time, I need a bigger crossover frequency, right? If I want to reduce my steady state error, I need high gain at low frequency, and achieving high gain at low frequency may often push the crossover frequency to the right. So all of the things we've been discussing so far tend to push the crossover frequency to the right. But it's important to realise that there will be limits on how far you can push the crossover frequency to the right, because of the need to roll off the complementary sensitivity function at frequencies where you might have substantial measurement noise or substantial multiplicative modelling uncertainty. Okay, so it's important to bear in mind that you're trying to, with the design of 1 degree of freedom, satisfy lots of different objectives, not just steady state objectives, not just transient objectives, but robustness to modelling uncertainty objectives, and reduction of sensitivity to measurement noise objectives. Okay, so that's why I started off with this picture looking like this, where we have lower and upper bounds on the crossover frequency. And control system design becomes hard when these lower and upper bounds on the crossover frequency are close together. Right? We have to make a transition from high gain to low gain. And if we're having to make that transition, through a narrow band, the slope is necessarily going to be steep. Right? The closer these bounds are together, the steeper the transition will be. Right? If they're far apart, we can do stuff like this and make the transition not steep. But if these are close together, it necessarily has to be steep to go through. Right? And it turns out that there's a relationship between how steep the transition is and the phase, and therefore the phase margin that you achieve. Right? Remember, the phase margin is about the phase of the open loop transfer function at the crossover frequency. So that's what this analysis is showing, right? And we're just showing the analysis for the case where the open loop transfer function is stable, right? and has no zeros in the right half plane. It can be generalised to accommodate unstable open loop transfer functions and right half plane zeros, but it's this relationship becomes more complicated. But in this special case, which is not uncommon, you can see that there's a relationship between the phase at a given frequency and the magnitude. And this is just a property of analytic functions. It comes from Cauchy's integral theorem again. All right, and what you can see is that, and really this is looking at, because there's a log here, it's looking at the slope, right, of the Bode plot, right? So on a log scale at a given frequency, right? So if you look inside here, if nu is this variable here, and if you're substituting here, this is really just j omega naught, j omega, right? And so what we're doing is doing this integral across frequency, right? And it's a weighted integral of the slope of the magnitude of the open loop transfer function, right? And this is what the weight looks like. So it's telling you that in terms of what the phase is at a given frequency, the slope of that function, the magnitude of that function, is most important around that frequency, right? So most of the weight is concentrated around that frequency, right? 0 here results when you put omega equal to omega naught, giving you 1, so log of 1 is 0. All right, so it's telling you that the phase at a given frequency depends a lot on the slope around that frequency. Right? And if you work out what this integral is and say, well, if I denote the slope at a given frequency by minus L, right, then this is giving you bounds on the phase. Right? So this is called Bode's gain phase relationship, right? And the key thing to take away is not the details of this, that's not what I'm trying to get across. I'm trying to get across the fact that there's a relationship between the slope and the phase. The bigger the slope, right, the closer the phase will be to minus 180. So when the slope is 1 on a log scale, right, then you're going to get a phase of the open loop transfer function that's close to minus 90 degrees, right? So for the slope of the open loop magnitude of the open loop transfer function at the crossover frequency is close to 1, you'll get a phase of minus 90. That's a phase margin of 90 degrees. That's a massive phase margin, right? You're not going to get any oscillations in your closed loop response. But if you had a slope of 2, right, and it's the slope of the log plot, right, then your phase will be minus 180. You'll have no phase margin. So the trick is to try to make the transition here with a slope that is less than 2. And your ability to do that is determined by how far apart these things are. So the closer they are together, the harder it is to achieve a good phase margin, right? But when designing these things, you want to make sure that the slope here is not too steep, because the steeper it is, the worse your phase margin will be, right? How are we easing off the slope here? Well, if you look what's happening here, this is going down like this. How am I bringing it up like this? A lead compensator will do that, right? If I've got something that's going down and I multiply by something like that, right, it's going to bring it up. So again, you can see that what a lead compensator can help you do is, by lining it up in the right way with the desired crossover frequency, is to make sure that the slope is not too steep at the crossover frequency. All right? And this is justification for doing that sort of thing. All right? So you want to make sure that, you know, the slope of the magnitude plot of the open loop transfer function is not much more than 1. Okay? If it's 2, then you're going to have nearly 0 phase margin. If it's 3, you're going to be on the wrong side of minus 180 degrees. Okay? So, you know, don't get caught up in the detail here. That's not the important thing. It's what you can conclude from this, right? And it's giving you a guideline for design. It's saying, you know, when trying to design this, make sure it's not the crossover is not too steep. All right? So it's another example of how analysis can inform design decisions, which is precisely why engineers study mathematics. Okay, so one way of designing a controller on the basis of a desired loop shape is just to choose the controller to be the desired loop shape divided by the plant model, right? Because, you know, the open loop transfer function is just the product of the controller and the plant transfer functions. So if I know what this is and I know what this is, I can just choose C to be this divided by this. Okay, so this example here, you know, involves a transfer function for an aircraft where there's some rigid body dynamics with quite good damping, okay, and then some flexible modes. All right, so this is the Bodie plot, and you can see that, you know, there's the zero causes this to happen, and then the resonant pole causes that to happen. Now, you know, you want to design a control system so that this sort of stuff doesn't get excited when you're operating the system, right? Because, you know, if you start exciting the bending modes of the aircraft, it might start doing this and it'll snap eventually, right? So you want to avoid that. So, you know, let's say that this is a desirable loop shape. It'll set the crossover frequency to be well below the resonant modes, okay? Because it's a first order system, we'll have a phase margin of 90 degrees, right? Because the phase of this is never less than minus 90, right? You know, it's chosen in this way with the gain to be 10 here to ensure that, you know, for frequencies around here, we haven't got much gain, right? So that'll mean we won't excite these modes when we're operating the system. And, you know, the reality is we've thrown away a lot of other modes. There's not just the first bending mode, there'll be second, third, fourth, fifth, and we've thrown all those away. That's giving rise to high frequency modelling uncertainty, right? And the way we can deal with that is by making sure that the open loop transfer function has gain that's much, much less than 1 at the frequencies where there's significant modelling uncertainty, right? So that's another motivation for rolling off well below where these things are. All right. The result of choosing a controller in this way here would be to have a very deep notch at the resonance. It's like you almost cancel it out. But, you know, your model's probably a little bit wrong. And so if it doesn't line up with what you're cancelling out, you can still get significant gain in that frequency. And one approach is to not cancel it out exactly, right, which is what we're doing here. We're not cancelling out exactly. You see, the open loop transfer function retains that mode, but it cancels out with a zero that doesn't quite have the same damping because it's got a bigger damping and the notch is not as deep, right? It's wider and doesn't go down. And so that will give you more robustness to uncertainty in the natural frequency and damping of this guy here, right? But in order to ensure that the gain is less than 1 at these frequencies, we have to sacrifice a bit of DC gain. All right? But this is just another way, you know, of choosing a controller given a plant model and a desired loop shape. Okay? This is just looking at, you know, the impact of unstable poles, right? So we're in a situation where we have a desired loop shape, okay? And it's looking at what happens when we add a pole, all right, without changing the magnitude part of the plot, where the pole is in the right half plane, right? So we're saying we've got a desired loop shape here, all right? And now we're going to say, well, if, you know, and you might say it's desirable mainly by looking at the magnitude plot. And you can see here we've got quite a good phase margin, nearly 90 degrees, okay? And then we say, well, let's suppose that our system has an additional pole that's unstable. What's the impact of that pole? That pole, so you're putting a zero and a pole here so that we don't change the magnitude plot, so this is just going to change the phase plot. How's it going to change the phase plot? Well, it's the phase of this at zero frequency starts off at minus 180 degrees, right? Because the sign of this is negative when you put s equals 0 in here, right? And at high frequency, it will go up to 0, right? How it does that depends on the location of P. For a small value of P, it will start like this and go up like this, right? For a larger value of P, it will start there and go like this, okay? So if P is less than the corresponding the crossover frequency for this desirable loop shape, you can see that the additional phase lag introduced by this, inserting the unstable pole in a way that doesn't change the magnitude plot, will not be so bad, right? You're only getting this extra phase lag, which will, sure, reduce your phase margin, but it's not going to make you unstable, right? Whereas if P is larger than the crossover frequency, you can see that we're getting a lot of extra phase lag introduced by this, which is going to push us on the wrong side of minus 180, right, leading to instability. Okay, so this is really suggesting that you need to have large gain, right, at frequencies that correspond to the frequency of where an unstable pole will roll off. Okay, which we've seen before via the time domain integral constraints towards the end of part 3 of the notes. Okay, so it's just confirming this. You can do similar analysis from the perspective of what happens if I put an unstable 0 in without changing the magnitude plot, right, to see the impact of having a 0. So we're putting it in such a way that the phase introduced by including this right half plane 0 is always negative, so it's always going to be reducing your phase margin, right? How much is it going to reduce depends on where the location of that right half plane 0 is relative to the crossover frequency, right? If it's such that it's much bigger than the crossover frequency, then you hardly get any phase lag, so it's not going to change things very much. So that suggests that you need the crossover frequency to be much less than the frequency associated with, the unstable 0 kicking up in the magnitude plot, okay, which is consistent with what we saw before, that the loop gain crossover frequency should be less than the real part of a right half plane 0, right? You need to have low gain in your open loop transfer function at frequencies where you have a right half plane 0. Right, so right half plane 0s put a limit, an upper bound on your crossover frequency, right? Whereas right half plane poles put a lower bound on your crossover frequency. We've seen those things before via different sort of analysis. So if you like, this is just confirming what we've seen before, but from a slightly different perspective. So, this is just a summary of all the things we've been discussing. I think the main point to take away is that there are no recipes. All right, we can use these simply parameterized compensator forms to help us adjust things in different frequency bands to achieve our specifications. All right, but at the end of the day, what we're doing here is loop shaping. We're shaping the open loop transfer function to meet specifications by choosing the controller parameters. And, it's a bit of an art. Design is not just, plug numbers into formulas. We need to train engineers because there's more to design than just plugging numbers into formulas. Computers plug numbers into formulas better than human beings. So it can't be just about that. All right, but what's important is to understand, what crossover means, what phase margin means, what having enough gain at low frequency means, and how that can be achieved by choosing the parameters of particular compensator forms. All right, what we'll do on Tuesday next week is look at one final method for designing controllers, which allows you to place the closed loop poles wherever you like. Okay, so it seems like a very appealing approach to control system design, but again, I'm going to present it in a way where I highlight, the pitfalls, right? And the main pitfall associated with pole placement methods is that the closed loop response is not just a function of the poles, it's a function of the closed loop zeros. So if you put all your attention, as well as the closed loop poles, so if you put all of your attention on the closed loop poles, you're not looking at the whole picture. Okay, so there's while it seems like an appealing method, it's actually hard to use. All right, we'll look at that. That'll be the last thing we look at. Then we'll look at problem set 5, and then maybe look at an exam, and then we'll be the end of the semester.
But this figure, you mean that one the third and fourth equals to
So
minus 1 and
here,
1?
here 1 is less than here the crossover frequency is 2, right? So when it's 1, so less than the crossover frequency,
Yeah.
you can see that the phase lag here is not much,
Yeah.
and it's less than the phase margin. So even when you